Hi everyone, this is our final presentation for Cone 319. We're team ACDC++. I'm Alexa.
I'm Colin.
And I'm David.
So our main motivation and objective with this project was specifically during this pandemic, the affordability and feasibility of long distance travel through airlines predominantly has become increasingly difficult. As a result, our proposed solution to this and finding minimum prices and most cost-effective methods is using a parallelized graphing algorithm where the nodes act as destinations and the prices act as the weighted paths. The data sets we use are one specifically from the Bureau of Transportation Statistics, each of 300 points from the years 2018 and 2021 respectively. In addition, since we weren't able to find any supplementary data sets with airfares, we used the class pre-generated data sets of 1,000 points, 2,500 points, 5,000, and 10,000 points specifically for OMP only. So in going forward, we initially wanted to use Dijkstra's shortest path algorithm. However, we noticed it was from one node to all nodes, as acting as the source node from finding all shortest paths. However, since airlines act as a destination between multiple nodes or multiple destinations and points, we employed the Floyd-Warshall algorithm instead, as the ratio is all to all. Furthermore, negative edges can be allowed. So as you can see here to the left, the top image illustrates the pseudocode for the algorithm that we implemented. Furthermore, below here is the visualization of the implementation of this algorithm. So k equals 0 looks at all of the node paths as is, and then k equals 1 is the intermediary node, which searches for the shortest paths and improvements upon the adjacency matrix, and then k equals 2 through 3 through 4, etc., and further improves upon that.
So for our project, we focused on two languages or frameworks. The first framework, which we selected, was OpenMP. And since Floyd-Warshall is an O of V cubed algorithm, OpenMP's parallel for directives can really make parallelizing nested for loops easy. And then for Julia, so Julia is a high-level language that focuses on high performance and developer productivity. And similar to C, Julia has what they call macros, and macros are very similar to C's directives. And Julia has a built-in multi-threading library whose macros look and behave similarly to OpenMP directives. So the benefit of Julia is you don't need an additional library such as OpenMP. It's just built into the main library. And then, of course, our parallelization. So if you look at the top left image, that is our OpenMP parallelization algorithm. If you remove the two pragma lines, you'll actually get the serial code where you have k, which is the intermediary nodes. And then for intermediary node, you're going to look at all the paths through this node and update the adjacency matrix as we go along. The beauty of OpenMP is not only does it leverage C's fork join model, it does implement loop collapse, which would unroll these two nested for loops within the K outer loop, turning it from what was originally an O of V squared time efficiency to O of V. And then because we're just parallelizing the inner for loops and not the K outer loop, there's no need to make the editing of the adjacency matrix a critical section, nor is synchronization allowed, and thus decreasing the overhead, but also yielding a fair amount of speed up. And then for the Julia code looks very similar to the OpenMP code. You have the K outer loop, and then you have the @threads macro surrounding the for J loop, as well as the for I loop. Our code actually takes inspiration from another library called Julia Graphs. And we actually employed an optimization. So we identified that if you can see in the top image, there's the float other equals graph plus graph, right? And if the first graph indexing is infinity, then the entire thing is infinity. So we don't need to calculate the other half of it. And if, knowing that, we can actually skip the loop completely and just remove the branching and any form of actual writing.
Cool. Moving on to some of our methodology and results, we did experiments across our primary two data sets for the 2018 year and the 2021 year. And then in order to just visualize speed up better, we also included a 1,000, 2,500 data set, as well as a 5,000 data set. Then beyond that, we also did speed up graphs for individually OMP results. We had our own Julia results. And then the last one is the Julia graphs library and their algorithm. So just using theirs as basically a benchmark for our own Julia solution. But yeah, I think the one big takeaway from a lot of these graphs is that the Julia solution, both ours and the Julia graphs solution, really struggled when it came to the smaller data sets. So you can see in the 2018 and the 2021, just the overhead from the threads, the time for both of those were so low that the overhead was really the majority of the work there. And so for the Julia implementations, they really struggle. But then, you look at the 2,500 data set and the 5,000 data set, and you see that clearly Julia does a lot better. Even so much so that on the 5,000 data set, you can see that the Julia solution, our implementation in blue, is really close to that OMP solution. So it just shows that as you scale, it gets closer, which kind of leads us into our analysis and our conclusion. So generally, OMP worked well across all the data sets and processes, and really was consistent with the smaller problems and the larger problems. But that being said, not to just completely trash Julia, Julia implementations worked really well in the large data sets. So when you take a step back and you think about the goals of Julia in general, Julia really wants to solve some of those machine learning, some of those big data problems while maintaining developer efficiency. So you still kind of get that efficiency where you want it on some of those big data problems. But that being said, there's still a lot of optimization that can happen in terms of the overhead with Julia. Yeah, another thing I wanted to mention was our Julia solution works better than the Julia graphs implementation. This is because of a few optimizations we did, specifically removing the path reconstruction as our problem didn't need that part of the algorithm. Moving on to recommendations. Generally, we would still probably recommend OpenMP, but just because it was more consistent and it still maintained the efficiency, slightly edging out Julia. But that being said, I think it's really a question of where your developer knowledge lies. So if you have a bunch of C++ developers, it probably makes more sense to do OpenMP, but I think having that higher level Julia language can be useful. If you do have a bunch of Julia developers, I think it's still really efficient. Yeah, in terms of future work, one of the big things I wanted to bring up was optimizing the timing mechanism, specifically with Julia. Those 2018 and 2021 data sets were the time to calculate those were so small that I felt like maybe with Julia, it was worth experimenting with other benchmark tools just to see if that error lies within the timing mechanism rather than the algorithm itself. Additionally, I wanted to experiment with the alternate parallelization strategies. There's another one that we researched that has something closer to an MPI solution that relies on a broadcast and then a wait for each of the threads. And the last thing I wanted to mention was we came up with some recommendations for the graphs.jl library, which is that Julia graphs library we found. They actually have two separate implementations of the Floyd-Warshall algorithm, one for the serial and one for parallel. And we found that running the parallel implementation is actually faster on a single thread because of that infinity checking optimization that Colin mentioned. So we plan on writing something on their GitHub, whether it's a pull request or an issue or a ticket, whatever it is, to see if we can have our project result in an optimization like that. So cool. Always, this is our bibliography, and thanks for listening.